Welcome to the Deep Dive, where we take your sources and unpack fascinating topics, really digging into the core ideas. Today, we're looking at something quite fundamental in mathematics, a set that's, well, simple to describe but has some truly mind-bending properties, the Cantor set. Yeah, we've got a mix of materials here, academic texts, lecture notes laying out the steps, and even a community discussion digging into the weirder side of it. So our goal today is to walk through these sources, understand how this thing is built, explore why it's so counterintuitive, and really see why it's, foundational stuff in analysis and topology. And joining me to help navigate this abstract terrain is our expert guide.
Glad to be here. It's a brilliant topic, and yeah, the sources give us a great path. The Cantor set really is one of those things that shows how abstract math can uncover truths our intuition might miss, especially about infinity and space. Let's build it.
Okay, let's do it. Construction. The sources mostly talk about the standard one, right? The Cantor ternary set.
That's the one. We start simple. Just the closed interval from 0 to 1 on the number line. Think of it like a solid bar, length 1, step 0, basically.
Okay. A line segment, 0, 1, solid.
Exactly. Now, the process is iterative.
Yeah.
Step 1, we remove the open middle third. That's the interval between 13 and 23. So 13, 23.
Open, so not including the endpoints 13 and 23 themselves.
Precisely. That's crucial later. So removing 13, 23 leaves us with two smaller closed intervals.
Yeah.
0, 13, and 23, 1, like chopping out the middle section. Your sources probably have pictures showing this.
Yeah, I see. 2 pieces left, and then we just keep doing that.
You got it. Step 2, apply the exact same rule to each piece we have left. So take the middle third out of 0, 13, that's 19, 29, gone. And the middle third out of 23, 1 next has 79, 89, gone.
Okay, so now we have 4 pieces. 0, 19, 29, 13, 23, 79, and 89, 1.
Exactly. 4 segments. And notice they're shorter.
Right, so the number of segments doubles each time, and the length of each segment gets divided by 3.
Precisely. At step n, you have 2 nuller segments, each of length 13 nullers. And the key thing is, this process goes on infinitely.
Infinitely, wow.
So the Cantor set, often called C, is the set of points that never get removed in this infinite process. It's what's left in the limit. Or, more formally, it's the intersection of all the sets of points remaining at each step, C, C, C0, and so on.
Okay, so it's what survives this infinite removal. It really feels like there shouldn't be much left at all.
That's the intuitive trap. And this is where it gets fascinating. To really understand what points do remain, the sources correctly point us to thinking in base 3, or ternary.
Right. Base 10 is normal. Computers use base 2. Binary. Ternary uses digits 0, 1, and 2. How does that unlock the Cantor set?
It gives a remarkably clean description. A number x between 0 and 1 is in the Cantor set if and only if it has a ternary representation using only the digits 0 and 2.
Only 0s and 2s. No one's allowed anywhere in its base 3 expansion.
That's the rule. Think about it. Step 1 removes the interval, 13, 23. In ternary, 13 is 0.1 and 23 is 0.2. The numbers strictly between them are those whose ternary expansion starts with 0.1.
Okay, so removing the first middle third gets rid of anything that has to start with 0.1.
Exactly. Then in the next step, we remove 19, 29, and 79, 89. In ternary, 19 is 0.01, 29 is 0.02, 79 is 0.21, 89 is 0.22. The removed intervals correspond to numbers whose second ternary digit must be a 1.
I see. The removal process systematically eliminates any number that, at some point in its ternary expansion, requires a 1 point.
Precisely. Let's take an example from the sources. Consider 14. In base 3, that's 0.020202. Repeating.
Only 0s and 2s. Okay.
So by the rule, 14 is in the Cantor set.
And importantly, 14 isn't one of the endpoints, like 13 or 23, right?
Correct. It's a point inside the set, not an endpoint to remove the interval. Now, what about those endpoints, like 13? Well, in ternary, 13 can be written as 0.1 exactly, or it can be written as 0.0222. Repeating.
Like how 0.999 equals 1 in base 10.
Exactly that kind of ambiguity. Since 13 can be written using only 0s and 2s as 0.0222, it satisfies the condition and is in the Cantor set.
Okay, I see.
Same for 23. It could be 0.2 or 0.1222. Because it can be written as 0.200 using only 0s and 2s, it's in the set too. Remember, we removed open intervals.
Right, so the endpoints were never actually thrown out.
Never. They always remain, and they always have a ternary expansion with only 0s and 2s. So all endpoints of all removed intervals are in the Cantor set.
Okay, so the Cantor set is precisely the set of numbers in 0, one whose ternary representation can be written using only the digits 0 and 2. That's surprisingly concrete.
It is. And this definition is the key that unlocks its let's say, paradoxical properties.
Right. This is where our intuition starts to fray. Let's talk about the size of the set. First, in terms of length, or what mathematicians call measure.
Yes, measure theory gives us a rigorous way to talk about length. The starting interval 0, 1 has measure 1. What's the measure of the Cantor set? Well, we can figure it out by adding up the lengths of everything we removed.
Okay. Step 1, we removed one interval of length 13.
Right. Step 2, we removed 2 intervals, each of length 13 raised to length 19. So that's a total length of 29 removed in that step.
Step 3 would be 4 intervals, each length 13 miracles, 1 equals in 27. So 427 removed.
Keep going. The total length removed is the sum of an infinite series. 13 plus 29 plus 427 plus 881 plus a.
That looks like a geometric series.
It is. The first term a is 13 and the common ratio r is 23.
And the sum of an infinite geometric series is a 1r, provided r 1. So 13, 123.
Which is 1. Wait.
Yeah.
The total length of all the bits we took out adds up to 1, the entire length of the original interval.
Exactly. So the measure of the Cantor set itself, what's left over is the original measure minus the total measure removed. That's 1, 1 equals 0.
0. So the Cantor set has 0 length. It occupies no space on the number line in that sense.
Correct. The sources call it a set of measure 0 or a null set. It's negligible in terms of length. Okay, that's paradox number 1, 0 length. It feels like almost nothing should be left. So maybe just a countable number of points, like just those endpoints we talked about. There's infinitely many of them, but it's a countable infinity, right?
That would seem logical, wouldn't it? But here's the kicker. Maybe Cantor's most stunning result related to this set. Despite having measure 0, the Cantor set is uncountable.
Uncountable, meaning it has as many points as the original interval 0, 1, or even the entire real number line.
Yes. It has the same cardinality, the same size of infinity as the interval 0, 1. That's the cardinality of the continuum, denoted by C of dollars. Far, far more points than the countable infinity of endpoints.
Hold on. How can a set with 0 length contain just as many points as a segment that clearly does have length? That seems fundamentally wrong.
It shatters our everyday intuition, doesn't it?
But we can demonstrate it using that ternary representation. Remember, every point x in the Cantor set has a ternary expansion, 0 tant c euros, using only 0s and 2s.
Right, only 0s and 2s. Okay, now define a mapping, a function. Take a point x from the Cantor set. Look at its ternary expansion, the one with only 0s and 2s. Now, create a new sequence by replacing every digit 2 with a 1.
So 0, 0, or 0 or 2 becomes iro b, where bane is can, so 0 or 1.
Exactly. Now, interpret this new sequence, 0, bane, biero, as a binary base-to-do representation of a number.
Okay. So like our earlier example, 14 is 0.02020202 in ternary. Replacing 2s with 1s gives 0.010101, and we read that as a binary number.
Yes, and that binary number corresponds to a unique point in the interval 0, 1. What's amazing is that this mapping is surjective. Every single number in the interval 0, 1 has a binary representation, and therefore it can be obtained from some point in the Cantor set via this replace 2s with 1s mapping.
So you're saying for any point you pick between 0 and 1, you can find a point in the Cantor set that maps onto it using this rule.
Precisely. We have a function that maps the Cantor set onto the entire interval 0, 1. Now, the Cantor set is a subset of 0, 1. And there's a theorem, the Cantor-Bernstein-Schroeder theorem, the sources mention, which basically says if you can map set A onto set B, and A is a subset of B, or it can be mapped injectively into B, then A and B must have the same cardinality.
So because the Cantor set is inside 0, 1, but we can map it onto all of 0, 1, they have to have the same number of points, the same cardinality.
That's the logic. The mapping isn't perfectly one-to-one. Actually, some endpoints in the Cantor set map to the same binary number, like 13, 0.0222, and 29.0200. Both map to binary 0.01, which is 14. But the fact it's surjective onto 0, 1 is enough, combined with it being a subset, to prove the cardinalities are equal.
0 length, but uncountably infinite points. Okay. My intuition is officially broken. What else can we say about the structure of this set? How are these points arranged?
Topologically, it's fascinating. First, it's nowhere dense. This means it doesn't contain any interval, no matter how small. You can't find even a tiny continuous piece of the line inside the Cantor set. It's all gaps, essentially.
It's like dust scattered on the line.
That's a great analogy one of the sources use. Mathematical dust. It aligns with the 0 measure, no substance, no density.
But it's an uncountable amount of dust.
Exactly. And here's another seeming contradiction. Despite being nowhere dense, it's a perfect set.
Perfect. What does that mean here?
2 things. First, it's topologically closed. It contains all its limit points. If you have a sequence of points in the Cantor set that converge, the point they converge to is also in the Cantor set. This makes sense because we defined it as an intersection of closed intervals, or as the complement of the open intervals we removed.
Okay, closed. And the second thing?
It has no isolated points. Pick any point in the Cantor set. You can zoom in as close as you like around that point, and you'll always find other points from the Cantor set nearby. No point is sitting out there on its own with empty space around it relative to the set itself.
So the dust is clumpy, infinitely clumpy, even though it's nowhere dense overall.
Yeah, that's a good way to think about it. Infinitely finely clustered, it's also totally disconnected.
Totally disconnected.
It means between any two distinct points in the Cantor set, you can essentially slosh the set into two separate pieces containing those points. More formally, you can find disjoint open sets separating them. Think back to the ternary digits. Any two different points must differ at some digit, and you can use that difference to separate them.
And compact. I think the sources mentioned that too.
Yes, it is. On the real line, compact means closed and bounded. The Cantor set is contained within 0, 1, so it's bounded, and we just said it's closed. Compactness is a very powerful property in analysis. In fact, topologically, the Cantor set is quite special. It's essentially the only example of a non-empty, perfect, totally disconnected, compact metric space. Any space with those properties looks topologically just like the Cantor set.
Wow. So this specific construction leads to a unique topological object. What about variations? You mentioned the ternary set. Can you do it differently?
Absolutely. You don't have to remove the middle third. You could remove, say, the middle fifth at each stage. You'd still get a set with measure 0, still uncountable, still nowhere dense and perfect. But your sources also mention something called fat Cantor sets. This is where things get even stranger. You can design the removal process, maybe removing smaller and smaller proportions at each step, such that the total length removed is less than 1.
Meaning the set that's left over?
As positive measure. You can construct a set that is still nowhere dense, contains no intervals, and totally disconnected topologically just like the standard Cantor set, but it actually has a non-zero length on the number line.
A Cantor set with length? That's wild. What about in higher dimensions?
Yes, that leads to what's often called Cantor dust. You get it by taking the Cartesian product of the Cantor set with itself. CXC gives you a set in the 2D plane.
So points x, y, where both x and y are in the Cantor set.
Exactly, or CXC in 3D space. These sets look like scattered dust, hence the name. They have 0 area in 2D, or 0 volume in 3D. They're nowhere dense, totally disconnected, but still uncountable. They're fundamental examples of fractals.
Ah, fractals. The Cantor set is often called the prototype fractal, isn't it?
It really is.
Yeah.
Key idea in fractals is self-similarity. If you zoom in on a piece of a fractal, it looks like the whole thing may be scaled or rotated. The Cantor set exhibits this perfectly because of the iterative construction. Remove the middle third, then remove the middle third of what's left. And so on any piece of the Cantor set, if you magnify it appropriately, looks exactly like the entire set.
Like Russian dolls. Almost.
In a way. The sources mentioned Benoit Mandelbrot, the father of fractal geometry, using an analogy of curdling, like how milk curdles. The material concentrates into smaller and smaller self-similar clumps.
So 0 length, uncountable points, self-similar fractal structure. Are there any other sort of bizarre operational properties? Like what happens if you add or subtract points from it?
There's a really surprising result mentioned in the sources. If you take the set of all possible differences between 2 points in the Cantor set, CC, meaning all numbers of the form x, y, where x and y are in C, you get the entire interval from omega to 1 to 1.
The whole interval, omega to 1. You can generate any number in that range just by subtracting 2 points from this 0 length dust.
Astonishing, isn't it? It shows how densely packed, in a sense, those uncountable points must be, even though the set has no length.
Definitely counterintuitive. And didn't you mention something related called the devil's staircase?
Ah, yes, the Cantor function. It's built directly on the Cantor set construction. Remember that mapping we used for cardinality? Turning 0, 2 digits into binary 0, 1. We can extend that idea carefully to define a function over the entire interval 0, 1. Let's call it fx. This function has some remarkable properties. It's continuous everywhere on 0, 1. It's non-decreasing. It never goes down as x increases. And it maps the interval 0, 1 onto the interval 0, 1, starting at f0 and ending at f1, 1.
Okay. Sounds fairly normal so far.
Yeah.
Continuous non-decreasing goes from 0 to 1. Where's the devil?
The devil is in the details of how it increases. The function is constant on every single one of those open intervals that we removed during the Cantor set construction.
Constant. So on 1323, the function's value doesn't change.
Exactly. And on 1929, it's constant. And on 79, 89, it's constant. On all the infinitely many removed intervals, which together have a total length of 1, the function is flat.
But it has to get from 0 to 1 somehow. If it's flat on all those intervals, where does it actually increase?
It increases only on the points of the Cantor set itself. The entire rise from 0 to 1 happens across that measure 0, nowhere dense set of points. The graph looks like a staircase, but with infinitely many steps, and all the vertical climbing happens instantaneously over the dust of the Cantor set, while the steps themselves, the removed intervals, are perfectly flat.
Whoa, so it climbs from 0 to 1, but its derivative is 0 almost everywhere on all the removed intervals.
Right.
Yeah, that earns the name Devil's Staircase.
It does. And interestingly, as your sources note, the composer György Ligeti wrote a famous piano etude called L'Escalier du Diable, inspired by this very function, trying to capture its strange, self-similar climbing nature in music.
Math-inspiring art. That brings us maybe to the human side. Jörg Cantor himself, he was a pivotal figure, right? But faced some opposition.
Immensely pivotal, and yes, significant opposition. His work in the late 1800s on set theory, especially the theories of different sizes of infinity, transfinite numbers, and constructions like this set, was revolutionary. But it challenged deeply held beliefs about infinity. Figures like Leopold Kronecker were fiercely opposed, arguing against the notion of actual or completed infinities.
So Cantor was dealing with infinities that were sort of finished sets, not just processes that go on forever.
Exactly, and Kronecker and others found that unacceptable. Cantor faced a lot of professional resistance, which sadly took a personal toll. It was a difficult period for him.
But his ideas ultimately won out.
Absolutely, they became foundational. David Hilbert famously defended Cantor's work, saying, "No one shall expel us from the paradise which Cantor has created for us." Set theory, transfinite arithmetic, these are pillars of modern mathematics now.
So bringing it back to someone listening today, okay, it's a cool mathematical curiosity full of paradoxes, but why does it matter outside of pure math? What's the relevance?
Well, the techniques and concepts are surprisingly far-reaching. Take Cantor's diagonal argument, which proves the reals are uncountable, and underlies the Cantor set's uncountability. That argument is fundamental in probability theory.
How so?
Probability relies on countable additivity. The probability of a union of a countable number of disjoint events is the sum of their probabilities. Your sources mentioned the dartboard example. The probability of hitting any single point is 0. If you could just sum up those zeros to the uncountable number of points on the board, you'd get 0 probability of hitting the board at all, which is absurd.
So Cantor's distinction between countable and uncountable infinities is baked into the rules of probability.
Deeply. It prevents paradoxes. And that same diagonal argument pops up crucially in theoretical computer science. Alan Turing used it to prove the halting problem is undecidable.
The problem of whether you can tell if any given computer program will ever stop running.
That's the one. Turing showed, using a Cantor-style diagonalization, that no general algorithm can exist to solve the halting problem for all possible programs. This established fundamental limits on what computers can theoretically do. Your sources even hint at connections to fields like formal verification, or maybe even the limits of virus detection areas dealing with the scope and limitations of computation.
So from this weird set made by cutting out middle thirds, we get insights into probability, the limits of computation. That's quite a reach.
It really is. It shows how exploring these abstract mathematical structures, even ones that seem like monsters defying intuition, can lead to profound understanding with very practical implications down the line.
So wrapping up this deep dive, we started with the simple rule, remove the middle third, repeat forever. And we ended up with the Cantor set. 0 length, yet as many points as a continuous line. Nowhere dense like dust, but perfect, with no points isolated. Totally disconnected, yet self-similar like a fractal.
It truly is a cornerstone object in topology and analysis. A fundamental example of a fractal, yes, and the concepts behind it, especially dealing with different sizes of infinity and using clever representations like ternary echo through probability, computation, and beyond. It forces us really to refine our intuition about basic concepts like size and space.
It leaves you with that core question, doesn't it? How can something have no length but still contain such an immense, uncountable number of points? It just underscores how mathematical reality can be so much stranger and richer than our everyday experience suggests. Makes you wonder what other counterintuitive structures are out there just waiting to be discovered.